We build neural networks layer by layer to increase their capacity to learn complex functions. But if you simply stack dozens of these layers on top of each other, the structure can crumble. The model fails to learn anything. A standard 3-layer network converges smoothly, but pushed to 30 layers, the error rate flatlines. This stagnation is caused by backpropagation, specifically the chain rule. The error signal must flow backward from the output to adjust the input weights. To calculate errors, the chain rule multiplies the error gradients of every subsequent layer together. If these values are slightly less than 1, say 0.9, multiplying them across 30 layers triggers exponential decay. 0.9 becomes 0.81, shrinking as it moves. When the signal reaches the first layers, the value is 0, the vanishing gradient problem. The layers receive no update, freezing completely. The inverse is just as destructive. If gradients are slightly greater than 1, they compound and grow rapidly, traveling backward. This is the exploding gradient problem. The updates become so massive, they overshoot the optimal weights completely, destroying the network and causing system crashes. Depth is mathematically unstable by default. To make a deep neural network function, we must introduce structural interventions that preserve the error signal from the output all the way to the input. We can address exploding gradients with a straightforward structural patch, stopping the runaway values before they corrupt the weight matrices. This involves enforcing a hard mathematical ceiling on the magnitude of the gradient update during backpropagation. This establishes gradient clipping. We define a threshold, and if an error gradient exceeds that boundary, the algorithm intercepts it and scales it back. However, capping individual components alters the gradient's direction, sending the update off course. To fix this, clip norm scales the overall vector magnitude down to the threshold boundary while maintaining its original angle. Clip norm prevents the network from blowing up, but it is strictly a defensive measure. It does not rescue a signal that is dying out. To solve the vanishing gradient problem, we have to examine the activation function. The standard choice was the sigmoid function, which squashes any incoming value between 0 and 1. But gradients rely on the function's derivative, and the sigmoid derivative reveals a fatal mathematical flaw. Its absolute peak is exactly 0.25. No matter what input you feed into a sigmoid function, the maximum possible derivative is 1/4. Applying the chain rule to these capped values guarantees immediate exponential decay across multiple layers. To bypass this, we use the rectified linear unit, or ReLU, which outputs a 45-degree line for positive values. The derivative of this line is exactly 1. Multiplying by 1 preserves the gradient perfectly through infinite depth. There is a caveat, the dying ReLU problem. Negative inputs yield a derivative of 0, killing the signal. To counter this, variants like leaky ReLU introduce a slight negative slope to keep the math flowing. Swapping sigmoid for ReLU prevents the activation function from shrinking the gradient, but it doesn't solve how the network initializes. Before training begins, we face another architectural vulnerability, the starting state of the weight matrices. If a network's initial weights are drawn randomly from a standard normal distribution, the data's variance can expand or contract unpredictably at each layer. For a stable start, the variance of the outputs leaving a layer must equal the variance of the inputs entering it. Glorit initialization achieves this target. By averaging the number of incoming and outgoing connections, it calibrates the starting weight variance so data flows evenly. But there is an incompatibility between Glorit initialization and the ReLU activation function. Because ReLU zeroes out all negative numbers, it eliminates half of all data on average, cutting the signal variance in half as data passes through. We use He initialization as the specific mathematical patch for ReLU networks. He initialization scales the starting variance by a factor of 2. This compensates for the half of the data that ReLU will inevitably destroy. He initialization tunes the starting state of a ReLU network, ensuring the gradient signal is robust at step 0. Initialization only protects the network during its very first forward pass. As weights start updating during training, the distribution of the inputs feeding into deeper layers begins to warp and shift unpredictably. To solve this in real time, we apply a dynamic patch between layers called batch normalization. This equation shows the first phase of batch normalization. It mathematically forces the incoming data across a mini-batch to standardize to a mean of 0 and a variance of 1. But strict standardization is risky. Forcing a mean of 0 might wipe out useful learned representations. To prevent this, batch norm introduces two learnable parameters, gamma for scale and beta for shift. These parameters allow the network itself to learn the exact mean and variance it needs to function at that specific layer. Batch normalization ensures the signal will not vanish or explode, regardless of how deep the network gets or how much the weights shift during training. A deep network armed with ReLU, heat initialization, and batch normalization converges rapidly, reaching its target loss in far fewer epochs. This brings us to our final pathology, overfitting. This stabilized network has such high mathematical capacity that it can stop learning generalized rules and simply memorize the training data. To counter this, we use Dropout. This regularization technique deliberately handicaps the network's capacity during training. For every forward pass during a training batch, the algorithm disables a random percentage of neurons. This forces the model to learn robust, distributed representations. It can no longer rely on a few specific pathways to pass critical information. This handicap changes how we interpret the loss curves on our monitors. Usually, a model's training loss is expected to stay below its validation loss. But because Dropout only runs during training, the network is operating with missing neurons, which artificially inflates its training loss. This graph shows the result. During validation, the network operates at full capacity with all neurons active. This leads to performance that sits noticeably below the training line, appearing superior to the data the model is actually learning from. Modern deep neural networks rely on a sequence of specific mathematical interventions. We start with ReLU, apply heat initialization, add batch normalization, and finish with Dropout. These work together to protect the structural integrity of the learning signal from the first layer to the last.